very much for to the organizers for the invitation and this wonderful conference. So I'm talking about sub-Riemannian geometry and what happens in infinite dimensions. In particular, we will see that, well, a lot of difficulties arise, but they're interesting difficulties, I think. So it's worth mentioning. So we've already talked about sub-Riemannian geometry in this conference, but so my presentation is maybe a little different, so it can be a little more general. Basically, sub-Riemannian geometry is the study of control systems that are linear with respect to the control, with a cost that is quadratic with respect to the control. And the most basic example of a sub-Riemannian space is the Euclidean space, but equipped with the Heisenberg sub-Riemannian structure. So the first two coordinates move as we want completely independently, but the third coordinate satisfies some equation. So you have x dot equals u, y dot equals v, and u and v are the control. And then z dot equals half of vx minus uy. And the action is, so the cost is just half of the integral of u squared plus v squared. So this, now let's go to a more rigorous definition of exactly what this means and the framework in which I will be working. So I define a sub-Riemannian structure on a Banach manifold as a triple E, Xi, and G, where E is a smooth vector bundle on M, Xi is a smooth vector bundle morphism between E and Tm, and G is a smooth pre-inversion metric on E. So the structure is called strong when the metric G defines a Hilbert norm on each fiber, and weak in all other cases. So the difference with what we've seen up till now is that usually instead of defining this vector bundle morphism, we just define a smooth sub-bundle of the tangent bundle of M, but our case is more general because basically we don't, for example, in finite dimension, it would allow the dimension of the horizontal space to vary depending on the point, while still providing a smooth control system. So we can still apply calculus of variation very easily. But anyway, we still define delta here in our special case as the image of the vector morphism Xi, which is just a subset of Tm, and which is fiber by fiber vector space, but it's not a subbundle. Then a horizontal curve is a curve for which that can be lifted. So it's a curve on M that can be lifted to the vector bundle E in such a way that the velocity of Q satisfies the control system that I mentioned earlier. And a horizontal vector field is just a vector field that is tangent to the image of Xi at each point. Alright, so here are some examples of infinite dimensional sub-Riemannian spaces. A very simple one is an L2 product of Heisenberg groups or Heisenberg structures. So basically you just take a countable number of Heisenberg spaces. So it becomes a sequence of triplets, right? And horizontal curves are such that each triplet moves horizontally with respect to an independent Heisenberg structure. So that's kind of the simplest possible example of a Heisenberg group, of a infinite dimensional sub-Riemannian manifold, I would say. But I mean, with infinite codimensions. Anyway, a more complex example is that of a free two-step nilpotent group. So here you take M to be just a Hilbert space times the Hilbert space of bivectors on this Hilbert space, and then horizontal curves are curves such that the coordinates in the Hilbert space move as ever you want, but then the coordinates in lambda 2 of h moves by q of t wedge u of t. So it's nice to know that this space of bivectors is just completely isometric and isomorphic to the space of skew-symmetric Hilbert-Schmidt operators on, it shouldn't be an N, it should be an H. Okay, so we can do a little bit about that. You know, we can diagonalize them, or almost diagonalize them and stuff like that. And finally, one of the most interesting examples is that of the group of diffeomorphisms on a compact manifold. So you take a finite dimensional compact manifold, and you equip this manifold with a sub-Riemannian structure, right? And then you consider horizontal curves on the group of diffeomorphisms as a flow of time-dependent horizontal vector on the compact manifold itself. So that's one of the most interesting examples of this. Then we can define the length and action of a horizontal curve, as usual, using the metric. And also, well, since there might exist several controls that give the same horizontal curve, we can define the length of a curve independently of the control by taking just the infimum over all the lengths. But actually, for what I will do, just to simplify stuff, we will always assume that this control is unique, right? So these two lengths coincide. All results still holds, but it's easier for the notation to just assume that these two are the same. Also, you can define the action of the curve the same. Alright, and then you define the sub-Riemannian distance between 2 points as the infimum of lengths of horizontal curves that connect these 2 points. So it's a semi-distance on M, right? And it's always a true distance for strong structures, but you can find weak structures such that the distance becomes 0. So it's just a semi-distance. Also, the orbit of a point is the set of points that are within finite distance of this point, which just means the set of points that can be connected to Q0 by a horizontal curve. And finally, we define a geodesic as a curve which minimizes the action on small enough interval, right? So it's a horizontal curve that on small enough interval will have minimal action with fixed endpoints. Okay. Now, there are two main things that we start investigating when we do sub-Riemannian geometry. The first is the problem of controllability, right? So, what is the orbit of the point, and can the orbit be the whole space? And the second one is finding the geodesics. Okay. So I'm going to describe partially how to do both of those things. So, and we'll see that it's a little harder than in finite dimensions, right? So, take L, the Lie algebra generated by horizontal vector fields, right? So, we know that, so this can be identified as simply a subset of the tangent bundle. And we know that in finite dimensions, if this Lie algebra is equal to the entire tangent bundle, then the distance between any 2 points is finite, so any 2 points can be connected by a horizontal curve. And moreover, you have the ball box theorem, which tells you that the topology induced by the sub-Riemannian distance is the same as the intrinsic manifold topology. Right? So there are some results that tell you that the Hausdorff dimension is not the same. The topology itself is the same. However, so this exact statement is open, as far as I know, in infinite dimensions. However, it's actually not really a good statement. It's not really a good question to consider the Lie algebra generated by these horizontal vector fields, because it's generated in an algebraic way, right? So, for example, kind of like think of the space of polynomials, okay? And that can never be complete, but you're in a Banach space, right? So, in the end, except for very specific cases, it's not really useful to look at the Lie algebra. I mean, what I mean is, it's hard. It's not really. It's hard to expect this condition to be satisfied, right? Because L is generated algebraically, so and this is a Banach space. So usually it's going to be impossible to satisfy. For example, if you take the product of Heisenberg groups, you can actually check that the orbit of the origin is the set of triplets such that the first two coordinates are L2 sequences, so square summable, but the last triplet sequence, I mean the sequence of Zn is only summable, right? So it's a stronger condition, okay? And you only have a dense subset of the entire manifold with anti-interior. So we only have what is called approximate controllability. And actually, if you compute the Lie algebra generated by the horizontal vector space, the vector fields, you're going to see indeed that you are just dense inside the tangent bundle. So here's a result that dates from the 80s, which tells you actually what can be expected reasonably in this case, which is that if you have a connected space and the Lie algebra is dense in the tangent bundle, then every orbit is dense. So you have what is called approximate controllability. Okay? And this is a very easy condition to satisfy. Like you just, I mean, if you take kind of random examples, you're going to see that this is usually what happens. Okay, and it's a result that's been generalized to a much more general setting, which is that of convenient spaces by Grandmartina and which are basically kind of like Fréchet spaces, but even so Fréchet manifolds, but even more general. Now, actually, there is a nice condition, which is kind of, it feels a little trivial, but you'll see that it can still be useful. So I called it the strong Choroshevsky condition, but that's just a random name. You can call it anything. So I didn't write it completely here, but I wrote just the simplest example. So imagine that you have a horizontal vector field X, such that, so this one is fixed, right? And such that the tangent bundle is given just by the horizontal distribution plus a Lie bracket between X and the horizontal distribution. Then, if this is satisfied at a point Q, you can check that sub-Riemannian balls centered out at Q are neighborhoods of Q. Right? And so if this condition is satisfied everywhere, in particular, any 2 points can be connected by a horizontal curve. And moreover, the topology induced by the sub-Riemannian metric is coarser than the intrinsic topology of the manifold, and is equal for the case of strong metrics. So here are some examples where it can be applied. The first one is the case where basically you just take the product of Heisenberg groups, but you collapse all of the first sequence, right? So instead of having xn as a sequence, you have an x as the first variable, right? And then you just, and the rest behaves exactly as the Heisenberg group, right? So you have one vector for the x, one vector field for the x variable, which is just moving along x, and then a countable number of vector fields along the y and z variables. Right? And then you can check that the strong Choroshevsky condition is satisfied here for this vector field x given by my vector field here x naught. Right? You can check that every vector field z can be written as y1 plus bracket between x0 and y2, where y1 and should be y1 and y2, but anyway, they are both horizontal. Okay, so that's kind of the most trivial example where the condition is satisfied. One that is much less trivial is that of diffeomorphisms that move with horizontal flow compared to on a compact manifold, right? So this result, so on So if you consider K a compact manifold and delta a horizontal distribution inside this compact manifold that is bracket generating, then you can check that any HS diffeomorphism of K with, so HS Sobolev diffeomorphism with S big enough exponent is horizontally homotopic to the identity. And moreover, you get additional information on the topology induced by the corresponding sub-Riemannian distance. So this is a variant of a result by Agrachev and Caponito that we obtained last year with the manual. Okay, now that's all I have to say for now for exact controllability. I'm going to start investigating geodesics. And you will see that here also there's some nasty stuff that can happen. Okay, so first we define a set of horizontal curve that starts from Q naught as omega Q naught. And the endpoint mapping from Q naught as simply the mapping that to a certain horizontal curve associates its endpoint. Right? So it's a smooth mapping, and its image is the exacted orbit of Q naught. So I wrote lemma here, but that's actually a definition. There's no result here. I just defined what I call a normal extremal between 2 points Q naught and Q1 as basically a critical point of the action with a fixed endpoint. But what I mean by that is that literally if you take any C1 variation of the horizontal curve Q with fixed endpoint, then the differential of the action along this variation is equal to 0. Right? So it's a little bit of a different definition from what you usually expect, but there's a reason why I use it in this setting. Now, it's very easy to check that if you have a normal extremal in this sense, then if you take the function which to a horizontal curve associates its action and its endpoint, then the differential of this function at Q will not be surjective. It will not be onto. Or else you could use the implicit function theorem to check that you can find a curve with strictly less energy, strictly less action with fixed endpoint, a variation with strictly less energy and fixed endpoint. Now, once we know that the differential is not surjective, we have two possibilities. And the first one is the possibility that happens in finite dimensions. And it's the only possibility in finite dimensions, which is that the image of this differential is included in a closed subspace. Right? So if it's included in a closed subspace, then it is included in the zero set of a linear form. Right? So you can find non-zero Lagrange multiplier P lambda, where P is one form on TQ1n, and lambda is either 0 or 1, such that the pullback by the differential of the endpoint map of P is equal to lambda times the differential of the action. And then, in finite dimensions, once you have this characterization, you just use a Hamiltonian formulation to compute the adjoint of the differential of the endpoint, and you get a condition for this equality. Right? So we have two subcases in this first possibility. The first one is if lambda equals 1, in which case it is indeed a normal extremal. Right? It's obvious that if you have this that is satisfied, then this is also satisfied. And in this case, we can prove that Q is actually the projection of an integral curve of the symplectic gradient of the Hamiltonian of the structure. Right? And the Hamiltonian is computed like this. But it's usually much more easier. It has a much more simple expression when you have like finite dimensional regular sub-Riemannian manifold, but here it's a bit complex. And the second subcase is lambda equals 0, in which case, since the Lagrange multiplier has to be non-zero, P itself is not equal to 0. And so you have what is called a singular curve, that is a singular point of the endpoint mapping. And here it's not obvious that it will be a normal extremal. Actually, there are counterexamples where you have an abnormal curve that is not a normal extremal. But in infinite dimensions, there is a second possibility that breaks down everything, which is that the image of this differential is dense in R times TQ1n, in which case there is no known Hamiltonian formulation. It's something I called elusive geodesic because they kind of elude us, and we don't really know how to check them. So I just finished by stating first the following theorem, which tells you that for a strong structure, you always have a Hamiltonian geodesic flow on the cotangent bundle, and moreover, every projection of integral curves of this smooth symplectic gradient is an abnormal extremal, and it's actually a geodesic, so it will minimize the action between fixed and point. Now I want to end the talk by just a couple remarks on what can happen with elusive geodesics. So first of all, elusive geodesics do exist. We have examples where there are minimizing curves that do not satisfy Hamiltonian equation. But what you can see for a lot of those, not all of those, but a lot of those, is that if you restrict yourself to a stable, proper dense submanifold, you get a bigger cotangent space, and so you get more normal geodesics. So you turn geodesics that used to be elusive into normal geodesics. Right? So the question would be, is there a right cotangent space? But it's a difficult question because, it would have to have a very weird structure so far as I can tell. Second remark, there are actually examples of normal extremals which are nowhere locally minimizing. So I don't know if that happens in finite dimensions, but in infinite dimensions it happens even with just the product of Heisenberg groups. So, there you go. Yes, the end of my talk.
Let me one remark from Russian point of view.
Maybe you explain better. I don't understand the last thing you try to say. That elusive becomes not elusive if you change cotangent bundle. What does it mean? I don't know. You
Okay,
have a choice.
so here's
You
an
have
example.
some choice of cotangent bundles.
So here's an example.
Change topology somehow.
Yeah. So you look at the product, the Hamiltonian product of Heisenberg groups, right? And I told you that the orbit of zero is actually a dense subspace, right? It's L2 of nr2 times L1 times nr. Right? And now you restrict this structure to this dense subspace, which has a new topology, right? A stronger topology. And so when you look at its dual, then instead of taking L2 from n into R3, you get L2 times L infinity, which is much bigger. And actually, if you restrict yourself to this space, then you get all minimizing geodesics will be normal geodesics.
Oh, okay. So okay.
But the problem is if you look at just an infinite product of angle groups, right? Then the orbit will be something like L2 times L1 times L2 third. And here, when you take the topological dual, it doesn't work. You're still missing some stuff because L2 third is not convex.
So the message is that, as usually in the infinite dimension, you cannot work just with one topology. You
Exactly.
have to deal with simultaneously with different topologies.
Let me one remark. It must be not Joe Rashevsky serum, but Rashevsky Joe.
Oh, see.
Because Rashevsky published his paper 1 year earlier. Almost nobody wrote series.
No, it's a great success that Rashevsky is mentioned before Cho. The order is not so important. You can tell alphabetical, but it was a great success.